Hi, everyone. Let me begin with an apology. As I told you in the email, there was an emergency situation, and I couldn't make the live stream. What I've decided to do afterwards was rather than do it as a live stream, I'm just going to do this as a pre-recorded lecture, and you'll see it. So you're not going to have the opportunity to ask questions, but it isn't a total disaster. I was actually planning another live stream early next week because this topic is on voltage, current, resistance, and capacitance is quite long, and so I'm actually going to straddle it across these 2 weeks, and so I was going to do another live stream anyhow early next week. So yeah, you're not going to be able to ask questions now, but you will definitely have opportunity to ask questions then, and of course my office hours are always a possibility, and email as well. Okay, so let's just start. Okay, I was actually only planning to do one question, and it's a long question. These questions are kind of long, and I'm going to go through it in detail. And it's these resistance questions where you have multiple resistors, and you both in series and in parallel, and you apply a voltage across them, and you ask the question, what is the voltage drop and what is the current through each of the resistors? And these are difficult problems because you have to kind of start globally, or you have to start locally and build up and find a total resistance. And once you have that, then go backwards and find the current and voltage across each one of the resistors. So there's many steps to this, and it's not easy to quantify these steps. Okay, it's not easy to say, well, do this first, do that first. There's kind of a general rule about it. So I'm going to do this today for during this stream for resistors, and I'm going to do it again for capacitors, because capacitors and resistors, they're similar, but they work differently when they're in series and parallel, and so it's worth going through both. Now there's other questions too in this section about like building parallel plate capacitors, and also discharging through an RC circuit, and I will do that in the next live stream. Okay, so let's begin. I say given that you can see here, given that R1 is 100 ohms, R2 is 300 ohms, and R2 is 300 ohms and R3 is 400 ohms, find the total resistance and find the current and voltage across each resistor. And you say, well, where? In this circuit right here. Okay, so in that circuit right there, you can see you have 20 volts across the entire circuit, and you have R1 and R2, which are in parallel. This is parallel, and then R3 there, which is in series with the R1, R2. Okay, and so let's begin. The first question, and you saw this on the assignment. I'll lead you through these to help you a little bit. But the first thing in any of these problems is find the total resistance, or in the case of capacitors, it'll be find total capacitance. So we have to start inside the circuit at the individual levels and build up to find the total resistance. Okay, let's do that in the diagram here. What you do first is you begin by identifying whether or which resistors are purely in parallel or which ones are purely in in series. Okay, a common mistake, well, I wouldn't say common, but a mistake that's made is someone will draw this and they'll say, oh, those two are in series, but not really, because you see that junction there. That junction there doesn't make them purely in series. There's this extra circuit right, this extra resistor right there, which is actually not, it's breaking the pure series there. Okay, so now that's not where you want to start. You want to start with these two right there. Okay, so those two right there are purely in parallel, okay? There's no extra junction that, breaks the parallel or anything like that, okay? And we're going to call the effective resistance of both of these R1, 2, okay? And they are in parallel, all right? So let's go back to this and let's calculate R1, 2. Now, for resistors in parallel, it's the reciprocals that add. So you have R1, 2, like that, is going to equal the reciprocal of R1 plus the reciprocal of R2, like that. Okay, and so 1 over R1, 2 is going to equal 1 divided by R1 is 100 and R2 is 300, like that. And so that's going to equal, I need my calculator. All right, so 100 reciprocal plus 300 to the minus 1, and then that's this number right here, okay? But that's not R12, that's the reciprocal of R12, so now we take the reciprocal of that, and we get 75. There we go, 75 ohms. Okay, Great, we've got our first step. And actually, when you're doing these things, you can actually, like when you're like during a test, I would draw out the circuit. I'll give you the circuit picture, but I would draw it out and then start showing what parts of the circuit you've reduced. So then over here, R12, okay, what I would do is I would write R12 is equal to 75 ohms, like that, okay? And now you might actually want to redraw this and replace that entire thing in a circle there, okay, in the red circle. You might want to replace that with just one resistor. So this is what the next level of the circuit looks like that. And of course, you still got 20 volts across the whole circuit like that. Okay, and I should put 0 volts over here. This is still R3 because we haven't touched that, okay? But now those two that were in parallel, they have been effectively replaced by R12, which is 75, okay? 75 ohms. And R3 is, what did I say it is? It's 400? Yeah, 400 ohms, okay? So there we go, 400 ohms, all right? And now it's obvious that these two are in series. I mean, there's only two and they're one after the other, so they're in series. I'm going to call that effective resistance R1, 2, 3, like that. Okay, so let's go back to this here like that. Okay, and now what do we have? We have R1, 2, 3. That's going to equal R1, 2 plus R3, like that. Okay, so just remember, in series they add, and in parallel the reciprocals. Okay, like that. All right. So what makes one of the things that makes it different from capacitors is, for capacitors it's the opposite. Okay, parallel you add, and in series there's reciprocals add. That's one of the differences. The other difference, and you'll see that when I do the other one, the other difference is that here we're worried about the currents traveling through these resistors, where there it's the charge that accumulates on each of the capacitors. Okay, once the capacitors charge up, there's no more current. Okay, so I just mentioned that in passing. There's similarities, but there are differences. Okay, so all right. What's that going to equal? R1, 2, 3. That's going to equal R1, 2, which is 75, and R3, which is 400. You know what? I'm going to change that 400. If you don't mind, I'm going to change that, because otherwise we're not going to have a very interesting number. Let's change that 400 to 100. Okay, like that. Okay, so I'm making up these numbers as I go along. All right, so so this is 100, like that. Actually, let's make it, sorry, I'm changing my mind. Let's make it easy. 125, like that. 125. Okay, and by the way, this is how I make it, how I make tests. I'll come up with something and then I play with the numbers as I go along. And I purposely don't solve these problems beforehand to show you how I think them through. Okay, all right, so 75 plus 125 is 200 ohms, and there you go. There is the effective resistance. This answers question A. Okay, so question A, total resistance is 200 ohms. All right, great. It's the next part that gets hard. Okay, now it's especially hard if I don't break it up for you, and I didn't here. Okay, on the test and on the assignment, I kind of walk you through it. You know what you should calculate next by the order of the questions. But here you go. Geez, how am I going to find the current through and the voltage across each of the resistors? This seems like a rather difficult problem. And the way to do it is you start with the whole circuit. So let's go back to this diagram here like that. And this diagram now is effectively this diagram here. It's like just one resistor with 20 volts here. Okay, and 0 volts there like that. Okay, and that one resistor, how big is it? Well, it's at R123, and we found out that that resistor is 200 ohms. And I want to know, I didn't ask you to do this, but the first thing you should calculate is the current through this. And now it becomes trivial, right? Because you have a voltage, V, you have a resistance, R, and you have a current, I. Okay, and we can even call it total, but I'll do that in the next over here. Okay, so for part B, let me just move this up a bit for you. Let's start by calculating the total current in the circuit. Okay, and how do you do that? Well, I is equal to V divided by R. Okay, or usually I don't know why I tend to remember it as V is equal to IR, but it doesn't really matter. Like one is just a rearrangement of the other, but we actually want this form here. Okay, although in my mind I always just carry on V is equal to IR like that. Okay, and so this is I, and it's actually I total. Okay, and so I don't know. Let's just put total there like that. Okay, let's move that aside here. Okay, and so I total is going to equal your total V, which is 20 volts, and your total R. So even though here I wrote R, that's really R123, right? Because it's the total R in the circuit. And we said that that was 200 ohms. And you can see why I changed the value of that last resistor so that I get this very nice answer of 0.1. And what are the units? Amps, like that. So volt divided by an ohm is an amp, so it's 0.1 amps. Okay, or you might see this, you might see 100 milliamps. Okay, an amp is pretty big, so generally in the lab you work in milliamps. All right, well, now what? Well, let's go back to this. So this is where we start to work backwards now. Okay, so now we know that the current here, the total current, is 0.1 amps. Okay, and now what can you say? Well, the way current works is that like if the current is 0.1 amps um, uh, at any point in the circuit, well, now I'm going to say any point, but see, it's 0.1 amps here. But if I trace that current like everywhere along here, there was no place where the current split. Okay, so everywhere along a segment where the current doesn't split, the current is the same. Think of it like a river with water flowing through it. Okay, like if so many gallons of water flow per minute down a river, that rate isn't different at different parts of the river until the river splits, and then each tributary carries a certain amount. Okay, so when the current splits where there's a junction, which we'll see as we work through this problem, where there's a junction, this current will split. But that's 0.1 ohms there. It's 0.1 ohms even inside the resistor, and it's 0.1 ohms all the way through it, like all the way through here. Let me pick another color here. So from that 20 volts there, this blue line that I'm drawing, that's 0.1 amps, 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 all the way through there. Okay, so this circuit, though, is the same as that circuit. Okay, it's just with a reduced resistor in there. And so if it's 0.1 amps there, 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 all the way through. Okay, and so that blue line is 0.1 amps, like that. Okay, and now remember what we're trying to do. We're trying to find the current and the voltage across each resistor. Well, we have now the current through that resistor right there. Okay, we have the current through that resistor. It has to be 0.1 amps. Okay, we also have the current through that resistor, but that was a reduced resistor. That was the reduced resistor 1, 2. So we don't have it for 1, we don't have it for 2, we have it for the combined 1, 2. Okay, but right now we do have it for number 3. Let me switch to the other diagram right here. Okay, so now we know that the current right here is 0.1 amps. We know that the current here is, whoops, I didn't draw that right. Hold on. 0.1 amps. We know that the current right here is also 0.1 amps. And let me make my A a little better there. Okay. And we know that the current here is 0.1 amps, all the way around there like that. The current is 0.1 amps up to that junction. This is where it splits, and it's not 0.1 amps there, and it's not 0.1 amps there, okay? But it is before the junction, and it is after the junction. So we could just start to write this down. We could just go like back here, and we can say we determined that current through R3 is 100 milliamps, okay? And we don't know the current through R1 and R2, but we know the current through the combined R1, R2, okay? And that's also 100 milliamps. Okay, so back to maybe this diagram for just a second. That R12 right there, that reduced resistor R12 is carrying 100 milliamps, okay? But R1 by itself isn't, and R2 by itself isn't, okay? So anyhow, we could still write that down, okay? We can write down over here. Where's my thing? There it is, okay? Current through R12 is 100 milliamps, okay? Now what do we do? Well, if you know R3, and I told you that R3 is 125 ohms, okay, so we know that R3 is 125 ohms. And we know that the current through R3, we can even call it I3, is 100 amps, okay? You can say, well, what can I do with this information? Well, you can use this, V is equal to IR, right there, okay? You can use that locally. You can use it globally on the whole circuit. You can use it locally. So globally means on like where all the resistors are reduced, or locally means on any one individual resistors or segments of resistors, okay? And so here we have R3. We know that R3 has 125 ohms, and we know that I3 is 100 milliamps, okay? Or we better do it in MKS, 0.1 amps, like that. And so you know what we can say? The voltage across number 3, which we can call V3, is going to equal I3 times R3. And what's that going to be? Well, I3 is 0.1, and R3 is 125. My brain was jumping to the answer there. Okay, so I3 is 0.1 amps. I'll put the units in there just so you can see them. Okay, and this one is 125 ohms, and that's an MKS. Multiply them together, you're going to get 12.5 volts. Okay, so great. We know that the voltage drop across R3, V3, the voltage drop across, R3, yeah. The voltage drop across R3 is going to be 12.5 volts, okay? So you could go back to this diagram here, which is getting a bit messy now, and so let me clean it up a bit. Okay, let me clean it up a bit. Actually, let me clean it up a lot. There we go, okay? So now we know that the voltage from there to there, okay, that's the voltage across there, is 12.5 volts, okay? What do you think the voltage is from there to there? Well, if all the way across here it's 20 volts, okay, all the way across it's 20 volts, and this part here is 12.5 volts. Voltage you can think of as like when we say drop, that's a good metaphor. Voltage you could think of as like going downhill. So you know from here to here, okay, you're going downhill 20 volts, and this part of it is 12.5 volts. This part here must be the difference, 7.5 volts. Okay, let me clean that up. And so we know that this must be 7.5 volts, like that. We can actually calculate that in a different way too, okay? But first, we know that the sum of the two drops, that drop plus that drop, must equal 20 volts. If we know that that drop is 12.5, then by deduction, that drop there must be 7.5. Okay, so over here, we could say the voltage drop, current through R12 is that, and let's just put it over here. Voltage drop must be 7. Actually, we could call it V12 is equal to 7.5 volts, like that. Okay, so we could do it that way. We could also calculate that 7.5 volts a different way, and it's worth doing it to show you that it's consistent. So just like here, we had the voltage drop across 3. So let's start with this formula here. Okay, the voltage drop across 3 was the current through 3 and the resistance across 3. Here, the voltage drop across 1, 2 is going to be the current through 1, 2 and the resistance 1, 2. Okay, so the current through 1, 2 was what? Well, the current through 1, 2 is, that's through both of them, is 0.1 amps. Okay, don't think of that as the current through number 1 or the current through number 2. It's the current through both of them, okay, combined. Okay, and so that's 0.12. And what was the reduced resistance R12? Well, we found that the reduced resistance between 1 and 2 was 75 ohms. And so if I take that 75 ohms here and put it there, and I multiply 0.1 times 7.5, 0.1 multiplied by 75, I get 7.5, like that, volts. All right, great. And that's exactly what we predicted, okay? But we predicted it in a different way, okay? So let's, oh no, I forgot to switch screens. Well, there we go. Let me just do that again. I'll talk you through it. I apologize. I do this all the time. Here, let me scroll this back up. So the current through R12 is 100 milliamps, and the voltage drop must be 7.5 for the reasons we just predicted. Okay, that is from this diagram here. That, you know, if this drop was 12.5, then this drop must be 7.5. Okay, but we can also prove it because we could say, look, the voltage drop across 1,2 must be the current through 1,2 multiplied by the resistance 1,2. And again, that's reduced resistance, and that's the current through both of them, not just through one. The current through both of them is 0.1 amps. And the reduced resistance, you could see it up here where we calculated, was 75. And so I put that in there. And of course, when you multiply the two together, you get 7.5 volts, which is what we expected. Okay. I apologize. I forgot to switch screens there, but it wasn't too long. Okay. So, all right. Okay. So now what? Well, now, you know, we've answered. Remember, the question was find the current and voltage across resistors. Each resistor, we have the current through R3, it's 100 milliamps, and we have the voltage across R3, it's 12.5. It's the other two that we now have to solve. Okay, so let's go back to this, and I'm going to be careful not to make that same mistake again. I hate when I make that mistake because it, you know, you guys are looking at the same screen, you're wondering, what am I doing? So, well, if you watch the whole stream, I fix it. Okay, so anyhow, so over here in this diagram, we now have that this drop is 7.5 across the whole thing right there, like that. Okay, so 7.5. And remember, it's 7.5. It's like you're up. It's like a drop. So you're like basically up high here like that. And when you come across that resistor, you have to drop down to a lower voltage here like that. But on the other side, let me do that in red. You know, you're at the same height there, same voltage height there, and then you have a drop across there, and you come to the same height over there. The drop across R1 and the drop across R2 must be the same. Think of R1 and R2 as kind of like walking downhill. If you walk down R1 and you get to ground level, you walk down R2 and you get to ground level, well, then R1 and R2 must be just as high. Okay, there must be, you know, the drop across here must be just as much as the drop across there. Otherwise, how would you wind up at the same height? Like you're at the same height here, 20 volts, and you're 7.5 volts lower there. So you must have dropped 7.5 volts across if you go that way, but also 7.5 volts if you go across that way. That's a bit confusing sometimes, but there it is. So now we know that the voltage drop across R1 is 7.5, but the voltage drop across R2 is also 7.5 volts. Okay, so let's switch back to our other screen there, and I did forget this time. Okay, let's continue. So now we can say the voltage drop across R1 is 7.5 volts. Okay, and the voltage drop across R2 is 7.5 volts. Okay. So again, that might be confusing, but that's only because maybe you're thinking that they add or something like that. The currents will add, as you'll see, but the voltage drops have to be the same because you're starting at the same height, you're dropping to the same height, and so you know that drop must be the same whether you're going by one path or another path. It's like walking downhill. You're at the top of a mountain 100 feet high. Okay, you walk down one path and you get to the bottom. You must have walked down 100 feet. You take another path down. It might be a totally different shape path, but you still get to the same point in the bottom. You must again have walked downhill 100 feet. Okay, so great. Now what? Well, now we have the situation where we have R1, and I said that R1 was 100 ohms. Okay, like that. And the voltage across R1V1 is equal to 7.5. Okay, and so this time we can use V is equal to IR again. All right, we can use V equals IR, but this time we know different things. We know R and we know V, and it's I that we want to calculate. Okay, so just rearrange this, divide both sides by R. we'll get that it's this, okay? Uh, I is equal to V over R, and I hate writing it that way. I'm going to just turn it around. I is equal to V over R like that, okay? So that's the way we want to rearrange it for this one. And it's for number 1, so it's I1, V1, R1. And what's the voltage drop across V1? It's 7.5. And what's the resistance? 100 ohms. And so what's that current? That current is going to be, all right, and that's going to be in amps, okay? Converting that to milliamps, you move the decimal over 2, 1, 2, 3, like that, and that's going to be 75 milliamps, like that, okay? So remember, amps are MKS, and milliamps are the milliamps are the more common unit, okay? Although it's not MKS. All right, now what about this one? So for this one, we've got that, okay? And only it's not 1, it's 2, like that. And what's that going to equal? Well, V2, the drop across V2 is again 75, all right? But V2 is, if you remember from up here, V2, sorry, R2 was 300. R2 was 300, okay? And so if you do that, what's that going to equal? I'll do it on my calculator very quickly. It's going to be 0.25 milliamps. Yeah, I don't need my calculator for that. It's going to be this. All right, like that, okay? And that's going to equal 25 milliamps. All right, and so we're done. It doesn't look like we're done because the information is scattered everywhere, but we're done because I can write resistance here. I'll make a little chart here, voltage here, and current here, like that. And so R1 was 100 ohms. Let me just, whoops, what did I do here? Oh no, I can't seem to switch my oh no, I lost my I can't seem to switch back to my window. I have a very strange situation. Yeah, I can't get to my technology. How wonderful. There we go. I'm so sorry about that. What happened was the window minimized and I couldn't get it to unminimize, and technology. So back over here, remember that R1 was 100. Let me just cut and paste all these actually. Copy. Okay. Down here. Well, I've already got R1 there. But paste. Okay. So R1 was 100. R2 was 200, and R3 was 125, like that. The voltage drop across R1 we found was 7.5 volts. The voltage drop across R2 was also 7.5 volts, and the voltage drop across R3 we found to be 12.5 volts, okay? And the current here, the current through R1, yeah, R1 was, where was it here? It was 75 milliamps. We'll work in milliamps, okay? And this one was 25 milliamps, like that. And through R3 it is 100 milliamps, okay? So we've answered the question. We've answered it. Let's go back to the diagram and see what's happening, see if we can understand these numbers, okay? So back to the diagram here. Let me clean it up a bit. Okay, we now know, let me do this in that one was 100. Do it in blue. That was 100 ohms. This one was, I've forgotten already, what was it, 300? Yeah, 300. 300 ohms, like this. And R3 was 100 was 125. Okay, this is 125 ohms. Okay, we found that the effective resistance for the whole circuit was 200 amps. Okay, so this whole circuit was, sorry, 200 ohms. Okay, so the effective resistance for the thing was 200 ohms. As a result, the current, I'll do the current in red here. The current in red here was 100 milliamps. Okay, the current here is also 100 milliamps. Okay, the way you should read these diagrams is this, like that 20 volts and that 0 volt there. There's a battery in there that I didn't draw. Okay, but I explained that during the lecture. So, all right, so that's 100 amps and 100 amps. Now, what happens right here to the current? It splits. Part of that 100 amps goes this way, and part of that 100 amps goes that way. If you hadn't done the problem, all you know is that the sum of this current up here and this current down here, the sum of those two currents has got to be equal to 100, okay? But we now know from that chart that I just wrote, we now know that through R1 we have 75. So this is going to be 75 milliamps up here. And down here, this is going to be 25 milliamps. Okay. Does that add up to 100? Does 75 plus 25 add up to 100? It does, okay? And it kind of makes sense. Think about it. This is the smaller resistor. The smaller resistor resists the current less, so you're going to get more current going through that. So you get 75 going through the 100, okay? And you get 25 going through the 300. And also, you can see the ratio. The 300 is 3 times bigger than the 100 ohm. Okay, and so the current going through the 300 is 1/3 of what goes through the 100. Okay, so that's why this is 25 is 1/3 of 75. Okay, now that 75 persists to here, and that 25 persists to there. When they come together, they join up together there, and what do you get here? 100 amps. You're back to 100 amps. Okay, because the 75 and the 25 add up together. Okay. Great. So there you go. You've got the voltage drop, sorry, the current through all of those. Now we can do the voltage drops. The voltage drops using V is equal to IR. I'll do that in, I guess, blue here. The voltage drop from there to there. Okay. And no, not blue. Too much. Let me do, I don't know, green here. There we go. Might as well use the colors if I have them. The voltage drop from there to there. Well, now we have the resistance is 125, and we have that the current is 100, and we found that that voltage drop was 12.5 volts, like that. Okay, now over here we could do the voltage drop from there to there. We could say, what's the voltage drop across just this one? Well, across just the 100, it's 75 milliamps times 100. 75 times 100 is, well, 0.075 times 100 is 7.5, like this, volts. Okay. We could also do it here. We could also multiply 25 times 300, and we would also get 7.5 volts, okay? And so the voltage drop there is, across there is 7.5. And the sum of the two voltage drops, 7.5 plus 12.5, had better add up to the full voltage drop across the whole thing, and it does, okay? And so there you go. What you're seeing there in the diagram is the solved problem, okay? And I'll go over one more time, like kind of the steps to get there. But there's the diagram of the solved problem, and the equivalent of that diagram is this chart right here, okay? The chart I have highlighted, all right? So, you know, you've got, for each resistor, it's going to have a voltage drop across it and a current, all right? And this is basically how you solve the problems, okay? Now, what would change with other problems is the number of resistors might be different, their configurations might be different. Generally, I like to stick to 3 because with 3 you can get at both series and parallel. But you know, I think in the pre-recorded lecture, let me see here how many I did there. There I did 1, 2, 3, 4. Okay, so maybe 4 at most, but then it becomes just tedious. Okay, and so I tend not to do that on a test. All right, but there you go. Okay, let me just kind of summarize what we did there, because there were a lot of steps, and let's just summarize. Let me go back to this diagram. The first thing we did is we found the total resistance. Okay, and then once we found the total resistance, we were able to find, we had the total voltage, we had the total resistance, we were able to find the total current, and the total current through this thing, whoops, that's not red, this is red. Okay, the total current through it we found was 100 milliamps. What that means is the current leaving the battery here and the current entering the battery here is 100 milliamps. When it gets to a junction, like there, the current splits, and that complicates matters, okay? But if you can find any resistor which has the full current going through it, you've got the current through that resistor, and you've got the resistance of that resistor, you can find the voltage drop across that resistor. That's what we did with R3. Okay, that's why we picked on R3 first, because it was the one where we knew the current through it, because the current through R3 is the total current, and we knew R3 because I gave it to you, and you were able to find the voltage. Okay, so once we had the voltage drop across R3 here like that, okay, we were then able to find the voltage drop across R12. Okay, and we found that to be 7.5 volts. And then because these two were in parallel, we were able to say, okay, the voltage drop across R1 is 7.5 volts. We know the voltage, we know the resistance, and therefore we know the current through it, okay, because V is equal to IR. Great, and we found 75 amps. And then over here, we said, okay, for R2, same situation. We know the voltage drop across it. We know R2, so therefore we know the current through V is equal to IR. And then we were able to get this current and that current, okay? Then as a check, these two currents, they have to add up to 100. Because why? Because, there's the junction right there where they split and they come together right there. Okay, so 100 splits into 75, 25, and then comes back together into 100. All right, and so that we were able to solve that one. Okay, so at every point there's kind of two ways to, well, not at every point, but like when you start to get down to the details, there's usually two ways to do things, and it's good to do them both ways because they'll kind of be checks on one another. Okay, so for instance here, we found that this had to be 7.5 volts. We found that because this was 12.5, so that's one way. The other way was we knew the effective resistance for R12, okay, and it was 75 ohms. And so if the effective resistance across this part of the circuit is 75 ohms and the current across this part of the circuit is 100 milliamps, 75 ohms and 100 milliamps, that's 7.5 volts. And that's another way to get at the 7.5. Okay, so this number here, that 7.5, we had two ways to calculate it, and the 75 125, we had two ways to calculate it as well. And why is that good? Because it shows you that the whole thing is consistent. Okay, so yeah, spent a lot of time on that. Okay, I'm probably going to spend less time on the equivalent for capacitance, but it's really worth going through this. And if you didn't catch it, if you didn't understand what I did, go through the video again, okay, and then you'll be able to you'll see how these problems are solved. Okay, once you get the idea, then the pieces will fall together. There's no I can't really give you an algorithm because if I give you some other kind of topology to the circuit, then life gets more complicated. I'm going to show you a few topologies in a minute. Topologies just mean the way that they're hooked up. Okay, so just do it the way just the general approach is do the whole thing and then try to break it down into the smaller pieces. Always asking the question, where do I know the total current? Where do I know voltage drops and stuff like that? And then you'll be able to break it down. Okay, so before I end though, that's it for this problem. We've solved it. Before I end, let me just show you some different topologies, different ways of hooking up the circuit that you might see on a test. Okay, so let me make sure we're looking at the right screen. We are. I don't want to have that problem again. So here we go. One possibility, I'll just draw a bunch of them. I won't even give you some numbers. So the one we just did, let me just redo that one, is this situation. Okay. And then you've got another one there like that. Okay, that's a terrible drawing, but there you go. Okay, another possibility is this one with 3. Okay. And how is this one different? Well, for this one, you have to look at these two first as being in series, and then replacing that with this one here, replacing that one with an effective, and then doing those two in parallel. Okay, and that's kind of it for the non-trivial ones for 3. You can have this with 3, obviously, but this one is easy, right? Because it's just 3 in a row. And when you got 3 in a row, they're in series, all 3 of them. So you could just add them all up. Okay. The other one is 3 in parallel. So you could have this. Oh, I'm sorry. My diagrams are just terrible. Like that. Okay. And this one's, I wouldn't say this one's a little harder, but it's easier than the other ones, than these other two, okay? Because they're all 3 in parallel, okay? Great. So what about with 4? Well, with 4, you get a lot of possibilities. You could have this. I won't do them all because I think there's quite a few, and I don't want to throw them all at you, but you can have that, and then you can have this, and then you can have that. Like that, okay? And you say, how do you do that one? Well, these two are in parallel, and so you do those. And then these two are in parallel, and you do those. And then these two, that's one effective one, like that. And this is another effective resistor. Those two then, these two here, would then be in series, and so then you would do those two, okay? So there's one possibility. Here's another one. I think this is the one I did on the pre-recorded lecture. You have this, and then you have this, then you have this. Like that. And you go, geez, how do I do that one? Well, you start with these two. Okay. They are in parallel. And then remember, whenever I draw a red circle, think of that red circle as a new resistor. Okay. And so that red circle, just those two resistors within that red circle get replaced with one effective resistance. And then these two, that effective one, and then this one here are in series. And then these two, that one up there and that one, are in parallel like that, okay? And just like before, you have to look at voltage drops and then currents. For this one here, maybe it is worth looking at that one again in some detail. Let me just redraw it. Sorry for having to redraw it, but that's okay, because this one is a little trickier. Let me just sort of walk you through it. You say, geez, how would I do this one? Well, for this one, you see, the voltage drop across the whole thing. Okay, I didn't specify any numbers there, but the voltage drop across the whole thing. Okay, and so the voltage drop across that one. So the current through that, because once you know the voltage across a resistor, and once you know the resistance, you know the current. V is equal to IR. Okay. You also know the voltage through the whole circuit because you would have gotten the effective resistance. And so by subtracting subtracting this one from the total, the current through the top portion from the total, you get the current through that one. Okay. And then you have the current through that one, and you know the resistance for that one, so you're going to get the voltage for that one. And then you get the current going through there and the current going through there. Okay. You know the voltage drop from there to there. You know the voltage then, and the voltage drop from there to there must be the total voltage drop. So you know the voltage drop from there to there. You know that voltage drop, and you know that resistor. So you got the current in this segment, and you got the voltage resistance for that one, and so you got that current through there, and so then the problem unravels. Okay, hopefully I didn't go too fast through that one, but I just kind of wanted to show you the flow of it more than the details. The details are actually in the lecture if you want to see those, but this is the kind of the way you do it. You just sort of identify, where do I know, all the resistors, where do I know the V, then you find the I. Where do I know the I, then you find the V, and you keep working through the circuit that way, kind of starting from the outside working in, and you'll be able to solve it. Okay, so there we go. I apologize for that one little glitch there when I was on the wrong screen. Hopefully it didn't confuse people too much, but there it is. And again, I also apologize for not being able to do this as a live stream. I did it as a pre-recorded lecture, though, my fault, so I'll be more than happy to make myself available if you have any questions with this or other things. They're barring another possible emergency, which I doubt. There will be a full live stream next week, and I might even do it during the Tuesday during regular class time, so that I know that people are going to be available and be able to jump in on that. Okay, so there it is, and if you have any questions, email me or whatever. Okay, bye bye.